Hi everyone, welcome to another video in my series on computer systems. In this video, we'll take a look, we're going to start Module 2, and we're going to start taking a look at machine code. In this particular video, we'll basically just look at some basics, and then we'll expand over the next few videos and get a little more in detail. Now, if you're following along in the book from the first slide, this is from Chapter 3 in that Computer Systems book, Edition 3 of Computer Systems, A Programmer's Perspective. So before we dive into machine code, let's talk a little bit about the history of the machines themselves, right? And we're going to focus on Intel x86 processors. These pretty much dominate the laptop, desktop, server market. And they've been, over time, they've had this evolutionary design, right? They've evolved over time. They're backwards compatible up until the 8086, which was introduced way back in 1978. And as time goes on, they add more and more features. And we'll take a look at that in the next slide. We'll take a look at this evolution and how things have changed over the years. Now, this is a complex instruction set computer, or CISC, system, as opposed to a reduced instruction set computer, or RISC system. So you've got many different instructions, many different formats, but you're only going to worry about a small subset of these when we deal with Linux programs. So as we're coding in C, we don't have to worry necessarily about like what this entire instruction set looks like. But we do want to keep in mind that it's hard to match the performance of reduced instruction set computers, right? We've kind of know that RISC systems historically tend to be better as far as speed and power consumption, but Intel has actually managed to make a CISC systems that they match RISC processors in terms of speed, but maybe not so much for power. So let's take a look at some milestones in that evolution of the x86 that I mentioned on that last slide. Starting way back in 1978, like we mentioned, 8086. All right, this is the first 16-bit Intel processor. This is the basis for IBM PCs, for DOS, which when you think about DOS, if you're not familiar with that, it stood for Disk Operating System. You can kind of think about the command line in a Windows system. Imagine that's your only interface for the operating system. This was a text-only, command line-only interface for old school operating systems way back in the day. Now, the 386 came out in 1985. That was the first 32-bit Intel processor. And this added flat addressing, so now we're capable of running Unix. One thing I do want to mention, because we mentioned with the 8086, that was their first 16-bit processor. The 386 moved to 32-bit. Notice that with the Pentium 4 in 2004, this was their first 64-bit processor. So our processor word sizes are increasing over time, right? We start with 16-bit, go to 32, go to 64. We want to keep in mind, we want to remember that 16-bit, because when we talk machine code, when we talk about doing things in assembly, when we refer to a word in assembly, we're often referring to that 16-bit word length. So even though you're running on a 64-bit system, what you're actually dealing with there when you talk assembly are what are called quad words. So we have words at 16 bits, double words at 32 bits, and quad words at 64 bits. So we want to keep in mind that there's a difference between the processor word size and a word, the size of a word, or a double word, or a quad word when we deal with assembly. So please keep that in mind, and we just remember that quad word as we look at the assembly that we're going to be going through in this module. We're talking about a 64-bit value when we say quad word. We're talking about a 32-bit value when we say double word. And when we just talk about word, we're talking about a 16-bit size. But moving on, continuing on through time, in the Core 2 In 2006, we got the first multi-core Intel processor. And moving on to 2008, we got the Core i7, where we upped that up to 4 actual cores. Okay, with a brief history of x86 out of the way, let's talk about some definitions. We always want to make sure we understand what the words we're going to be using for the rest of the video mean. And so these are some things that we want to differentiate, that we want to make sure we understand and study this slide. Pause it if you need to. And make sure that you're familiar with what all of these words are talking about within this context, because they can be easy to get confused and mixed up a little bit, but it's going to be important that when we use one of these terms, we all know exactly what we're talking about. So let's start with architecture. It's also referred to as ISA, or instruction set architecture. This is the parts of a processor design that one needs to understand or write assembly or machine code. So the instruction set specification, what kind of, how many registers do you have? What are their size? What are they referred to as? Now, a microarchitecture is an implementation of the architecture. So when we start defining things like cache sizes and core frequency, we're talking about microarchitecture. Various forms of code. Now, so often we start out with something like Java or Python or C or C++, and these are very high-level languages. As we start getting closer to the processor, we get into assembly code or machine code. Now, machine code is actually the byte-level programs that a processor actually executes. This is the stuff that the processor actually understands. Because as we abstract more and more, we're getting closer and closer to things that are understandable by humans, right? We can just read this code and understand what's going on. The machine code, we have to go down a few levels to get down to the machine code so that the hardware can actually understand it. And with assembly code, we've got a text representation of machine code. So if you've looked at assembly code before, and we're going to be doing a lot of that in this video and the next few videos as well, it can look pretty technical and a little bit intimidating, but this, keep in mind, that's actually a higher level than what the processor understands. That's the first little step toward making things human readable, so that we're not just looking at a bunch of hex values and trying to figure out what's going on. Some examples of instruction set architectures would be the Intel x86, like we've talked about, the IA32, Itanium, x86-64, or ARM, which is used in almost all mobile phones. So let's talk about the programmer visible state of a computer when we're dealing with assembly or machine code. This is the stuff that, as programmers, we're going to access. We don't have to go all the way down to talk about transistors and what they're doing. What we want to keep our eye on and make sure we understand are the parts of the CPU and memory, of course, that we can kind of access, and that the stuff that we're doing is interacting with. So we've got the PC, or program counter, on the CPU, and all that does is hold the address of the next instruction. It's called the RIP in x86-64. Right? It's the instruction pointer. This is where we go to find out what's the address of the next instruction I need. We've got the register file, so the registers live here. This is heavily used program data, so this is where we can store some stuff that's going to be closest to the CPU. And then we have condition codes that store status information about the most recent arithmetic or logical operation. So when I do a compare of some sort, when I do an addition or a subtraction or a multiplication, when I do some kind of, again, arithmetic or logical operation, we set a bunch of different condition codes, and we'll be diving into exactly what those are and how we can use them for conditional branching. So when we jump around to various parts of our code, we'll actually use these condition codes, and we'll see that when we talk about jump instructions. Now, over on the right side here, when we talk about memory, memory is nothing more than a byte addressable array. You can think of it as a one-dimensional array. It's just a big old line of bits. and we can jump around to various addresses, to various points within this array, and put information into it or take information out of it, right? So this is going to store code. It's going to store user data. It's going to have a stack to support procedures, which we'll get into in a couple videos. And so we've got the CPU as sort of one piece and the memory as another piece, and we have information going back and forth between the two. We send addresses from the CPU out to the memory. We can also send data, so let's assume that we're writing some information out to memory. We send the address that it's going to live at, and then we send the data itself. We can also send an address to memory and get data back. So if I need to read something from memory, if I need to load that into the register so the CPU can work on it, I'll get data back, or I'll get instructions back, or some combination of the two. So this is how those two kind of most basic level things that we're going to look at for our purposes interact with each other. Now, let's do a brief review of what happens when we write a program in C and we want to turn it into object code. Right? So, I mean, normally we use GCC and we kind of skip a lot of intermediate steps. We can just tell GCC to, oh, hey, GCC in the name of my program. I might give it a -O flag so that I can specify the name of the executable. If I don't, I'll just get the executable as a.out. But when this is happening, there's actually several different steps that are going on, and it's good to know what's happening at every step of the process. So let's say we have code in files called p1.c and p2.c. We're going to compile that with GCC. Now we can do a -OG, which is a little bit new, not very new anymore, but this says use basic optimizations. Don't go nuts. Don't use our standard level of optimizations. Let's use basic optimizations. Then we specify our input values, p1.c and p2.c. And then, as I just said, this little -O tells us, okay, the executable is just going to be called P. So we start with our text, our C program. We can write it in a text editor, and we often do. A lot of people don't use IDEs for C. They just fire up a text editor and bang out their code that way. So we can use the compiler. We use GCC to get that down to an assembly program. Right, p1.s and p2.s. We've turned it from a C program to an assembly program, and that's just text as well. Then the assembler kicks in, and GCC will do this for us, or you could use something like AS, and that's going to give us an object program. That gives us our object files, p1.o and p2.o. And then finally, we use the linker where we're gonna add in static libraries that we've referenced, right? That kind of stuff gets linked in, and we end up with a binary file, and that's our actual executable program. That's our final process. Now, again, we usually just think in terms of using GCC with a single command to just go through all of this whole process in one command, and usually that doesn't matter. But if we want to be able to dive into the assembly, if we're getting into a debugging situation or an optimization situation where we need to dive into the assembly and really get a lower level view of what's going on, we can go ahead and compile it to assembly and dive into it that way, so that we can kick out the lower level assembly language representation and get a better idea, a more fine-grained look at what's actually happening with our program. So when we compile into assembly, we can take a very simple C code like sum.c that you see here on the left, and all we're doing is, well, we're just adding a couple things up and then saving it out to memory, right? But when we compile that into assembly, well, we get this other thing. We see that we have sum store in both, right? So we've actually got in the assembly, we've got the reference to the name of the function that we've made. But then we have all these push and mov and call and mov and pop and all this weird looking stuff, right? So don't worry about that right now. We're going to understand what all this means very soon, but this just gives you an idea of what we're looking at. This gets us, again, it's a lot closer. These Things that start with percent signs are actually references to registers. Okay, and then the push and move and pop are assembly commands. Then this will do what we've told it to do. This is the assembly for what we've written in C. So it's kind of just a translation into something, again, a lot closer to what the processor is actually going to do, what the processor understands. We've gotten a big step closer to our machine code. Now, again, this GCC command is going to produce a file called sum.s, but I want to warn you, you're going to get very different results, or you might get very different results on different machines, right? Various flavors of Linux, Mac OS. We have different versions of GCC. We have on Mac OS, we're in actually C-lang. And we have different compiler settings. So this is not going to be a one-to-one. We can't just take this exact code and go to a bunch of different machines and expect this same exact assembly to pop out. So we're going to be using for these lectures, we'll use sort of a very, very basic version of x86-64 assembly. But keep in mind that the things are going to look a little different from system to system. Now, let's take a look at that in action. You can see that I've just entered into a text editor. I've just entered that code from that last slide. And when I run that exact GCC command that we saw in the slide on it, what we get out is this. Whoa, this looks pretty confusing, right? Again, don't worry about it. We're going to go through and we're going to learn what this stuff means. But as you can see, we get something that looks very different from that sort of very standard assembly language that we're looking at in the slides. And this is just to demonstrate what I was talking about before. Different systems will give you different output for this. Now, this is actually running on Mac OS, but we can also fire up a Ubuntu Linux virtual machine here. And if we shuffle things around so we can compare a little bit, this is sum.s, just compiled with GCC again, but on a different operating system. And as you notice, there's a lot that's in common, right? We see some stuff that's actually the same thing. We've got, this MOV from RAX to RBX. Oh, well, hey, look at this. Oh, there it is. We can actually see that that's a one-to-one thing. We see that same exact instruction given in the assembly on both systems, but there's plenty of stuff that's different. It's organized a little differently. There's actually more commands over here that we can see. We can see more instructions than we do over on this side. So both of these programs accomplish the same thing. They do exactly the same thing, but when we compile it down to assembly, we can get different outputs based on what system we're on. But again, there's lots of commonalities, right? So these pushes and moves and calls, all of these things are going to be common to just about anything we do. So, like I said, we'll take a look at a generic view and make sure that you understand how all of those operations work. And that will give you the tools you need to go out there and sort of figure out what's happening regardless of what system you're on. So let's talk about a few more terms and ideas that we want to keep in mind as we begin our study of assembly. We have integer, and we put that in quotes, data of 1, 2, 4, or 8 bytes in length. These can be data values, or they can be addresses, which are untyped pointers. They can basically just point us to memory locations. We get floating point data of 4, 8, or 10 bytes. And if we think back to the representing numbers module in previous videos in this series, that makes sense, right? Single precision is 32 bits. That's our 4 bytes. Double precision for 64 bits, or that's our 8 bytes. And remember that we have, just on Intel systems, 80-bit floating point numbers, and that's our 10-byte floating points. When we talk about code, we're talking about byte sequences that encode series of instructions. So we're still just looking at a bunch of bits, but they're encoded and interpreted in such a way that they're going to give a series of instructions to the processor. Now, there are no aggregate data types such as arrays or structures in assembly. When we talk about an array, that's a high-level programming concept. When it gets down to the memory level, it's just contiguously allocated bytes in memory. So when we declare an array of the size that can hold 10 integers, we're just going to allocate in memory enough space to hold 10 integers, and we're going to keep it all together. So in assembly, no such thing as an array, no such thing as a struct. These are things that come in C and other high-level languages. So what are operations when we talk about assembly? What operations in assembly do are perform arithmetic functions on register or memory data. We can transfer data between memory and a register, so we can load data from memory into a register or store register data into memory. And we can transfer control. We can do jumps to and from procedures. We can do our conditional branches, so our if-then type things, right? We can even use those jumps to implement our loops. The operations take care of all of that kind of stuff for us. So thinking back to the steps that we go through when we compile code, right? We go from our raw C code into assembly. Then our next step is translating things into object code, and this is what the assembler does. Takes that .s and translates it into the .o. This gives us a binary encoding of each instruction, right? So at this point, we're just looking at a whole bunch of, well, we usually take a look at it in hex because that's easier to deal with. But at this point, we're just looking at a bunch of bits, right? We're just looking at numerical instructions or numerical representations of instructions. This is a nearly complete image of the executable code, but don't forget we have that final step where we go through the linker, and that's because in the object code, we're missing linkages between code and different files. So the linker resolves those references between files. We combines in static runtime libraries like malloc or printf, so when we include things that allow us to use memory allocation and input-output, this is what the linker's doing for us. And we want to keep in mind that some libraries are dynamically linked, and that means that linking occurs when the program begins to execute, and we generally specify those in the GCC. When we compile, we specify the dynamically linked libraries that can come in. We also have DLLs in Windows are an example of dynamically linked libraries that come in. And so we see these all over the place, right? This is ubiquitous. But at the general level, we just want to know the ideas of what these things are doing. This is what the linker does for us. It links these different files that can be in very different locations doing very different things, brings those into our final executable. So let's take a look at a concrete example of what all three of these levels kind of look like, all three of these steps in that compilation process. In the C code, we've got asterisk dest equals t. All right, that's just, of course, dest there is just a pointer. We're going to store the value t where we've designated by dest. So that's what, of course, that pointer thing does, is it takes the value of what's in the variable dest and treats that as a memory address, right? So we're going to say, hey, take the value of t and store it out at this particular location in memory. Now, the assembly, we're moving an 8-byte value to memory. Now that's quad words in x86 64 parlance. And remember, even if we're using a 64-bit processor word, remember that we use quad word for that because we're kind of giving a historical nod and calling a word the 16-bit value way back from the 8086 days. Now we're just going to use this move command. So this MOVQ just means move quad word. The %RAX and then to this %RBX in parentheses. Now, what in the world does that mean? That means we'll have at some point, okay, and we don't have to get too deeply into how this all gets loaded into the registers yet, but we'll have loaded into register RAX the value of t. Dest will be stored, or the value that's in the variable dest will be stored in register RBX. And what this does is move that out. The parentheses tell us to move it to the memory location. Okay, so if memory is this capital M, and that indicates an array, right? So we're going to have memory is just one big, huge array as far as the processor is concerned. So we're going to move that value in RAX. We're going to move T out to the memory indexed in at the location that's pointed at by RBX. All right, so RBX ends up being a pointer, right? That's our dest is a pointer. That's what we're treating it as. That's what this asterisk means. Well, RBX with those parentheses means put this out into memory at the location that I'm giving you within the parentheses, and what we're telling it to send it to, the location we're sending it to, is what's stored in RBX. Now, the object code is just this 3-byte instruction. It's stored at address 40059E. And as you see, we just have a few hex values, right? This is just pure binary. So the object code, we've gone all the way down to purely numerical representations, whereas in the C and the assembly, we've got some text that we can actually read and understand as human beings. Now, one really nice, handy tool that I would recommend playing with and getting familiar with is object dump, or obj dump. You can actually run this on either your complete executable or your .o file for your code, and it analyzes the bit pattern of a series of instructions and produces an approximate rendition of the assembly code. So that's what you see in this box up at the top here. You can actually see the addresses that the commands are stored at. Notice that these are, as in a previous slide mentioned, it's 1, 3, or 5 bytes long for each instruction. And it's going to lay out what the memory address is, what the instruction is, and just in hex. And then it's going to give you a rendition of what the assembly looks like. So this is a really handy way to get an idea of how various assembly instructions map to the object code. So definitely go through, fire up a terminal, write out some C code, go through the steps that we showed you before to get that down into a .o file or just to a complete executable, and run this obj dump on it. Take a look at that, get an idea of how these things map back and forth to each other. Another thing that I, again, really recommend that you do yourself, just to get a look at how this works, is we can use GDB to do something called disassembly. So we can actually start up GDB on our executable, and we can disassemble that procedure called sum store. And then we can examine the 14 bytes starting at sum store. So we can actually, in the object code, right, we just have that hex. We can go ahead and disassemble that. And once again, as you can see in the yellow box, we get that assembly out of it. So we can get a look at, again, how do these things map to each other? And also, if we're just dealing, this is something that people do to analyze code. If you just have an executable to work with, you can disassemble it, get yourself at least out to that assembly code, and start analyzing what's going on. So what can be disassembled? Well, really anything that can be interpreted as executable code. So, Windows executables, Linux executables, anything that can be interpreted can be disassembled, because the disassembler just examines bytes and reconstructs the assembly source. So we can take any executable and run it through this process and get that reconstructed assembly, but we want to keep in mind that there are legalities involved, right? So, for example, if we try to do this with WinWord, technically you could do this with the tools available, but reverse engineering, and that's what this is, right? This is reverse engineering, taking the executable and disassembling it to get reconstructed code. That's reverse engineering, and that's forbidden by the Microsoft End User License Agreement. So if you're using Windows, don't do this. Do not do this. That's forbidden by your End User License Agreement. Right? So you want to be a little careful. And, if you're going through and you're doing this stuff just to kind of play around and see what things look like, write your own code, please. It's going to be better for you educationally anyway, because, if you write some short, simple code that you can get a reasonably sized disassembly of, and then tie that all back and look at those comparisons to find out how they interact and how they map to each other, you'll actually understand what's going on. It's way better than doing something legally problematic that, you're not really going to get any benefit out of anyway, right? So please don't do that. Use these tools as a way to learn how assembly works and how the object code works and stuff, but do it with your own code. So let's take a look at these registers that we were just talking about. Now, you'll notice that there's a couple different ways that these are named, and it might seem a little confusing at first, but it all makes a ton of sense. And a lot of it has to do with the way Intel processors evolved. So way back in the days of 8086s, we had 8 registers, and those were AX through BP. And those are kind of reflected here, but those were 16-bit registers, right? 8086 was a 16-bit processor word. And now as we moved forward, we expanded our register sizes, right? We expanded those word sizes, so the sizes of the registers expanded. But we've actually kept things so that we can reference the lower order bytes as well. So for the top one here, RAX, we started out with just AX, and that was a 16-bit register. Then when 32-bit systems came along, we expanded that, and that was called EAX. So EAX here is the lower 32 bits of RAX, the entire register. The lower order 16 bits within EAX is just AX. Now, RAX is the quad word. That happened when we got to x86-64. We had to expand again. We went to 64-bit registers. So RAX, RBX refer to the full 64-bit quad word registers. EAX, EBX, etc. refer to the lower order 32 bits of each of those registers. AX, BX, etc. refer to the 16-bit words. Again, lowest order 16 bits are those AX and BX words. And then we can even get right down to the lowest order byte with AXL, BXL, etc. Now, what also came about with the evolution of the Intel processor are these other 8 registers, R8 through R15. And that's why we have a little bit of a different naming scheme, is because these came along later on in the process. So for R8, R9, etc., we have, for example, R8 is our full quad word 64-bit register. R8D will be our double word, or 32 bits. R8W would be a word, or 16 bits. And R8B will be the lowest order byte. Now, this figure shows the full breakdown of all that with all of the different areas that can be addressed. It also shows over on the right here what these registers are usually used for. Now, don't worry too much. We're actually going to go over what all of these terms mean. But for example, when you call a procedure and you give it arguments, the first argument would go into RDI or EDI or DI, right? It'll go and do some portion of the RDI register. The second argument would go into RSI. Something to keep in mind is RSP, our stack pointer. That's really important. We kind of want to stay away from that because that takes care of allowing us to use the stack for procedure calls and nested procedures and things like that, which, again, we'll get into that later on in the videos. But this is a great figure. It's in the book. If you're following along in Computer Systems: A Programmer's Perspective, this is actually in that book. It's in section 3.4, and this is actually figure 3.2. It's called integer registers. So this is a great thing to, if you don't have the book, screenshot it. If you do have the book, put a bookmark at that page, go find it, and make sure you know where that is, because we're going to refer back to this a lot moving forward. Well, now that we have an idea of what the registers look like, we should talk about moving data into and out of them. So let's take a look at the MOV command, the move command. Now, we see this as MOVQ. The Q just means we're dealing with quad words, and we just have the source and the destination that we specify. Now, there's several different types of operand that can go in for the source or the destination. Now, there's the immediate type. Now, that's constant integer data. So, for example, 0x400, right? So that's hex 400 minus 533, like a C constant, but it's prefixed with a $sign. So it's encoded with 1, 2, or 4 bytes. The register is one of 16 integer registers that we just saw. One example would be RAX or R13, and this percent sign indicates that we're dealing with a register. But again, RSP, that stack pointer, is reserved for special use, so we don't touch that. And the others have special uses for particular instructions. So we have to be familiar with what all of those kind of special cases and the uses where registers are going to get used for certain kinds of instructions, so that we don't end up doing something that messes up our program. Now, memory has 8 consecutive bytes of memory at an address given by the register. Because remember, we have a 64-bit processor word size. So for the memory, we've got 8 consecutive bytes, right? 64 bits. They live at certain addresses. And remember, we can just think of a memory address as an index of the memory array, because we just think of memory as one big array, right? The simplest example is this %RAX in parentheses. Remember what that does. It says go to the memory at the location that's pointed to by the value in RAX. So we just have some value in RAX, and that's going to be the index. That's going to be the memory address we want to go to. If we put that in parentheses, we're saying, go to this address in the memory. So, of course, there are several combinations that we can use with an MOV command. Now, notice this one says move L instead of move Q. So what does that mean? Well, the L just means that we're moving a 32-bit value. So that means we're moving a double word. So that's something to keep in mind too. Those different suffixes can tell you how much data you're moving around. But these combinations work just the same for the MOVQ, MOVL, MOVB, etc. So let's take a look at some of these examples. If we're going to go from move an immediate value, right, it's like a constant value into, well, either a register or into memory, we just specify the command MOV, Q, or L, or whatever. Then the constant, right, so 4 in hex or -147 decimal. Now, the destination, if we just specify the register name, %RAX, it's going to just get moved into that register. But when we move it to memory, we see, there's those parentheses again, right? So when you see those parentheses, think about the pointer. Think about the C analog. That's where we're using a pointer. So we're going to move that -147 into memory at the location reflected in what is in RAX. So RAX has the memory address stored in it. When we use these parentheses, we're saying this is the location in memory to put my source from the move command. When we move from a register to either a register or memory, it works the same way, right? The only difference is that for the source, we're going to specify the register that the value is coming from. If we move to a register, we just specify the register. If we're moving to memory, we put those parentheses around it. If we move from memory to a register, then we're just going to put the parentheses around the source. That's going to say go to the location in memory pointed to by the value in RAX and move that into register RDX. And once again, we see when we have those parentheses, we're also dealing with a pointer. Something to keep in mind, we cannot go memory to memory with a single instruction. We would have to pull something from memory into a register, then write it from that register back out to memory. We can't just specify 2 memory locations as our source and destination. So let's take a look at what that means in the general case by taking a look at a couple simple memory addressing modes. Now, in normal mode, we have R, and that's going to specify a register R. And if we put that in parentheses, that just means that register R is specifying a memory address. And again, that's pointer dereferencing in C. So if we're going to move from RCX in parentheses to RAX, That means we're taking whatever is in memory at the address stored in RCX and moving it into the RAX register. We can also add displacement. So if we have a displacement outside, right, preceding those parentheses and then the register inside those parentheses, the register specifies the start of a memory region that still has just a memory address, and constant displacement D specifies the offset. So when we go out to memory, we're going to say, start at the address stored in register R, but then add this offset to it to get to where we want to go. So in that case, if we have our memory address stored in RBP, when we do the move instruction, if we have that preceded by an 8, we're going to say, go to the address stored in RBP, add a displacement of 8, so go to the address plus 8, move what's there into the RDX register. So let's take a look at an example of how a very simple swap function in C ends up turning into assembly. And let's kind of go through this example and see exactly how this addressing works. So if I've got swap, and that just takes a couple parameters, a couple pointers, and I'm going to go ahead and declare a couple longs, T0 and T1, to store the values that are stored at, right? I'm going to take what is at the memory specified by XP and drop what's there into T0. I'll take what's stored at YP, drop that into T1. Then I'll just say, okay, put T1 into the memory location specified by XP, put T0 into the memory location specified by YP. I have now swapped those two values in memory, right? I've taken what lives at the address in XP and what lives at the address in YP, and I've just swapped them around. Nice and simple. What that translates to in assembly is we're going to move what's at the location in memory specified by what's in register RDI. Why? Well, remember from our figure when we were talking about registers, RDI stores what the first parameter, right? So XP is the first thing we passed in. RDI is going to store that. So we're going to move what's in memory at location RDI, move that into RAX. We'll take what's at memory location specified by RSI, because that's our second parameter, YP, move that to RDX. Then we'll move what's we just put into RDX out to the location specified in RDI. That's going from that register where we just put that information out to the location specified in RDI, which is, remember, XP. And then what's in RAX goes out to the location in YP. So this is a nice and easy example because it's a one-to-one. We have, for every single line in the C code, we have a single line in assembly. And then ret just means we're returning from the function call. So let's break this down step by step. This slide shows us kind of the initial conditions. Let's assume we've got whatever we have out in memory. We won't worry about the specific values that are out there yet or the specific addresses. The registers, RDI and RSI, are going to get those pointers, which means those are going to point to memory locations. And once we call this function, RDI is going to get XP, right? That's the first parameter. So the value XP goes into RDI, YP goes into RSI, RAX gets T0, and RDX gets T1. So let's go step by step through this and keep those registers and values in mind because that's important. We have to keep track of what variable and what parameter goes into which register kind of at the start of things so we can follow along through the process. So when we've called swap, we've passed in a couple of memory addresses. We've passed hex 120 in as XP and hex 100 in as YP. So those are going to end up corresponding to some of these addresses that we see over here in memory. And now we've got a couple values. We have 1, 2, 3 in address hex 120 and 4, 5, 6 in address hex 100. So let's go through this assembly line by line and see exactly what's happening. So our first command It's straightforward enough, and all of these are. It's not nearly as complicated as it looks, I promise. So our first command says move what is in location RDI in memory into RAX. So we look at RDI, and it has hex 120, so we go to address 120 in memory. Oh, there's 123 there, so that's going to get moved into the RAX register. So now RAX has 123 in it. For the next line, we do the same idea, right? We take a look, we see, oh, we have these parentheses, and we've got RSI inside them. That means we're going to go to take a look at what's in RSI. That's hex 100. And the parentheses mean, oh, let's go to that address in memory. We see that that has the value 456 stored at that location. So we move it to the destination, which we specified, which is the RDX register. So now the register RDX has the value 456. Now, in our third line and our fourth line, we're actually going to have those parentheses in a different spot, right? Because now we've got those values out of memory and into registers. Now we want to go ahead and move them from registers out to memory. So we'll take what's in register RDX and send that out to memory to the address specified by RDI. Now, RDI says, oh, hex 120. So we take the 456 that's in RDX and we move that out to memory at address 120. And then we do the same thing in the fourth line. We take what's in RAX, that 123, we move it out to the address specified by RSI, which is 100. So we make that move. Now what was originally at address 100 is at address 120, and what was originally at address 120 is down at address 100. So we've done our swap. And again, each of these commands maps one-to-one to one of the C commands. Now, that's not always going to be the case. A lot of C commands are going to end up mapping to big blocks of assembly, but this is a great little function to kind of get our feet wet and see how these addressing modes work and get an idea, or at least start to get an idea, of how assembly is actually doing things. So, we've seen this slide before, right? These are our simple memory addressing modes. So I hope we've got a good grasp on how these two different things work, but let's take a slightly more in-depth look at the kind of general case and really get an idea of what all of our different memory addressing modes look like. Now, our most general form, when we kind of complete our memory addressing mode general form, looks a little bit different, but it's very similar. We still have our displacement on the outside, then we have our parentheses, right? Because we're talking about memory addressing mode, so we're going to be addressing memory. But now we have a few different things. Rather than just that R in the parentheses, we've got a few different things. So let's take a look at what these are. Again, D is that constant displacement that we're going to add at the end. RB is our base register. That can be any of the 16 integer registers that we saw in that figure before. RI will be our index register, which can be any register except for the stack pointer. Right? We don't mess with the stack pointer. Let's let that do what it does. And S is a scale factor. It's going to be 1, 2, 4, or 8. And we think about why might it be 1, 2, 4, or 8. Well, the simplest explanation is we're just dealing with binary, right? So we're not going to scale something by 5. We're not going to scale something by 7. We're not going to scale something by something that doesn't fit into a binary representation or fit neatly into a binary representation. But that's not the entirety of it, but we'll put a pin in that and think about this moving forward. We're going to kind of build our answer to why that scale should be a 1, 2, 4, or 8 as we move along. So keep that one in mind. Keep that question in the front of your mind as we move through the rest of these videos. Now, how does this work? What we've got is, it's pretty simple. We have the value in our base register, RB. We add to that the scale times the value of the index register, RI, and then we just add the displacement. So it's very similar. All we really did with that D parentheses R was we specified a base register. We just didn't specify an index register or a scale factor. So that still fits this form. That simpler mode that we just saw still fits into this general form. We just didn't specify, again, the index register and the scale factor. Now, we have some special cases. If we just do RB comma RI, it's just going to be RB plus RI. If we didn't specify a scale factor, we'll assume the scale factor to be 1. So the default for S is 1. If we have the displacement and the RB and the RI, then we just do RB plus RI plus D. If we specify RB, RI, and S without the displacement, we go ahead, we just fill in what we have into the general form, right? We'll have RB plus S times RI, but notice that D has a different default than S. If we don't specify a D, we default it to 0, and that's why it doesn't show up in this last example, right? In that special case, we didn't specify a D, so we assume it to be 0. In the first case and the second case, we didn't specify S, so we assume it to be 1. Because if we assumed S to be 0, then the index register, which we specified in both of those examples, would have just dropped out. That would have zeroed that out. Instead, we're still adding what's in the index register. That means that the default scale value, the assumed scale value, is 1. The assumed displacement value is 0. So that's just something to keep in mind and be a little careful of. Make sure that you are aware of what the defaults are for D and S and why. So let's take a look at some examples of this stuff in action, right? Let's get some actual addresses here and figure out where we're going in memory. So let's say that we have hex F000 in RDX and 0100 in RCX. Okay, we just a couple registers floating around out there. These are the values that are in them. So let's take a look at some expressions that use these memory addressing cases and just work out exactly how those go. So for the first one, we have, well, what do we have? We have a displacement, hex 8, and a base register, RDX. So we're just going to follow our formula, right? We take the F000 that was in RDX, add to it the displacement, which is 8. We get a final address of F008, right? It's just that simple. If we specify, notice in the second one, we don't have a displacement and we don't have a scale factor. We just have a base register and an index register. What do we do in that case? We just add them. We default our displacement to 0 and our scale factor to 1. So we just effectively, we end up taking the values in those two registers and just adding them together. So F000 plus 100, F100, that's our final address. Our third example, we have a base register, an index register, and a scale factor, but no displacement. So we assume the displacement to be 0. We just, again, plug things into our formula. Our base register plus our scale factor of 4 times our index register of 100. 4 times 100 is 400. Add that to F00. Our final address is F400. Now, finally, we actually have a very interesting case where we didn't specify a base register. And that's fine, too. We add this little comma here to indicate that, that the spot for base register is blank. But again, we can still do the same thing. We don't have the base register, so there's nothing to add, but we do have a scale factor of 2. We do have an index register, RDX, which is F00. So 2 times F00 plus our 80, which is our displacement, ends up being 1E080, and you can check the math on the hex in that, but that still works. We just drop things into the formula for our general form, and out pops the address that we're trying to get to. Now, something you'll see with these memory addressing computations all the time is a command called LEA. That stands for Load Effective Address. Now we give it a source, which is an address mode expression like the stuff that we just went over, and we set the destination to the address denoted by the expression. Now, we can actually use this to compute addresses without a memory reference, but you'll see it a lot. You'll see a lot of disassembled code where you're using these LEA instructions, and you're not actually dealing with memory at all. You can actually use them to compute arithmetic expressions of the form x plus k to the y. So let's take a look at how we do that, right? How can that actually happen? How do we, by computing a memory address, do we actually do math? Well, when you think about it, we were doing math in that general form of memory addressing, weren't we? So the k here corresponds to the scale, so that can be 1, 2, 4, or 8. And let's take an example of what we can do here. If we just have this very, very simple little C code in the green box, right? We're just going to pass a value x into this function, and we're just going to return x times 12. This, all we're doing here is multiplying x by 12. Now, again, remember, multiplication can be expensive, right? So we can actually save some cycles by using load effective address. We can take the commands in yellow. Now, the load effective address, we're just going to go to this memory location, and we follow the same rules. RDI is our base register in this example. We're also going to use RDI as our index register and a scale factor of 2 with no displacement, right? We've just saw this, a bunch of different times. And we're going to take whatever that calculation ends up being and move it to RAX. And RAX, if, again, go back to that figure we looked at, that's our return register, right? That's where return values go to get returned. So what this ends up being equivalent to is, if we have x in RDI, because RDI is what gets that parameter, this is going to evaluate to x plus x times 2, right? The scale factor times the index register, which is x, plus the base register, which is also x plus x times 2. So we've basically calculated 3 times x. Now, this SALQ, that's just a shift left. We're going to shift left by 2, right? And put that into RAX. So what this does is take the destination, shift it by the source part of that command, the SAL command, and then put it back into the destination. So we're going to take 3x and shift it left twice. What does shifting left do? Well, remember, we can use shift to multiply by some power of 2. If we shift it twice, we're multiplying by 4. So, oh, look at that. We used LEA to calculate 3 times x, and then we used SAL to shift it left twice, which multiplies it by 4. That's our 12x, and our return value is sitting in RAX. So we've managed to do this mathematical computation by using our memory addressing scheme. But again, it had nothing to do with memory. We just sort of used it as a shortcut to do some math without actually dealing with memory at all. And like I said, you want to keep this in mind because it's a handy, handy tool. And again, when you take a look at assembly, you're going to see these LEA instructions all over the place. So you want to be careful that are we actually calculating an address out in memory to go do something to, or are we just using it as a shortcut to do some computations? So let's finish up this video by working through some C code that just does some simple arithmetic and see how that translates into assembly. And we're going to see that we'll use some LEAs and some SALs rather than the additions and multiplications that we might expect given what we're looking at. So let's just sort of take it line by line through the assembly. Now, first thing we want to keep in mind are what registers are used for what things. Now, arguments X, Y, and Z go into RDI, RSI, and RDX, and that's expected based on that figure that shows the usage of the registers from previously in the video. Now, RAX is going to, at various times, have the value of T1, of T2, and in our return value, RDX at a point during the process will get the value of T4, and RCX will get the value of T5. And we're going to see how assembly does things, can get clever in taking our C code and doing it in an efficient way. So the first thing we have is we're going to calculate T1, and that's just going to be X plus Y. Now remember, argument X went into RDI, argument Y went into RSI. But rather than using an add, we're just actually going to use a load effective address. We'll use an LEA. We'll use RDI as our base register, RSI as our index register. And remember, when we do this, we get the base register plus the index register. So this gives us X plus Y, and we'll move that into RAX. Our next line, we'll get T2, and we'll just actually use an add in that one. We'll add RDX, which is argument Z, right? So T2 equals Z plus T1. We've calculated T1 and moved it into RAX. So we take RDX, which holds the value of Z, add that to RAX. Well, there's T2. We've got Z plus T1. Now T3, we're going to put a pin in T3 for a second because it's a simple addition. And if you'll notice down in T5, we're actually going to use T3. So we can actually just replace that, right? We can just, instead of calculating T3 and then later on doing T3 plus T4, I can actually just calculate for T5 X plus 4 plus T4. And oh, hey, I'm pretty sure that's going to fit one of our memory addressing options as well. So let's move on to T4. We'll actually do a couple commands for that one because we're going to multiply Y by 48. Remember, Y lives in the register RSI because it was the second parameter. So if we use the LEA, do RSI as both the base and the index register with a scale factor of 2, right, we'll end up doing Y plus Y times 2. So that gives us 3Y. We'll move that into RDX. Now, we haven't actually finished calculating T4 yet because we just have 3Y. We have to get to 48Y. So what do? Well, let's shift it left. Let's multiply with a shift. Now, if we shift by 2 to the 4, that's 16. 16 times 3 is 48. So 3Y left shifted 4 times gives us that Y times 48. That's 16 times 3Y or 48Y. So, hey, we have T4, and that's living in RDX. Now we can move on to T5, where we'll just sort of sink T3 into the calculation. So we take a look at another LEA. We have a displacement of 4. RDI, which is argument X, is our base register. RDX, which remember, that's now T4, is going to be our index register. So our base register plus our index register plus our displacement gives us X plus 4 for the displacement. That's T3 is X plus 4 plus T4, which is now living in RDX, and we just calculated T5. Now, finally, we've done a multiplication earlier, but now when we have the T2 times T5, remember, T2 is now living in RAX. T5 is living in RCX. So we'll just multiply RCX by RAX, put the result into RAX. We now have our final return value living in RAX, which is our return register. So we're done. So again, this is where you're not necessarily just going to say, oh, I see an addition, so I'll look for add. I'll see a multiplication, so I'll look for MUL, right? That's not going to be a one-to-one because there are more efficient ways to do things. So that's something to keep in mind with assembly moving forward too. Keep in mind what things are doing, and you might have to get in and really dig into exactly what is in each register and what each of these commands does, because compilers are very clever. They're going to save cycles wherever they can. So This is a great example of where assembly is not necessarily going to look like a one-to-one match to what's going on in the C code. So when you walk away from this video, you should have an idea of the history of Intel processors and architectures and that evolutionary design that we talked about that gives us those weird little quirks and artifacts and registers that are named in different ways, things like that. You should have an idea of C assembly and machine code, how we go from one to the other. Some assembly basics like registers and operands, move instructions, and some basics on doing arithmetic. And we want to keep in mind that the C compiler will figure out different instruction combinations to carry out our computations. So again, remember right from that last slide, when you see an add, just a one thing plus another in C, you're not necessarily going to see an add instruction in the assembly. It might do something different to save some clock cycles.